So I will speak about malware and electromagnetic emanation. Why? But first I would like to introduce the context. So this work has been funded by the French Agency for the Research. The main coordinator is Annelie, my responsible as a postdoc, and the main contributor that could not come today due to visa problem is Pham, that is finishing his PhD, and the postdoc Matthew start also before me, and I follow them. And we are part of the capsule team in ERISA. So why side channel, why EM, and why IoT and malwares? So first, what we did is we tried and we did. We can determine a malware that is executing on IoT device using EM emanations. Why we did this? Because there is an explosion of the IoT, as everybody knows now, and also the malwares exploding this against these targets. But the challenge were all the evaluation techniques that are well known in the computer science community, and also others specific problems due to the complex environment, sometimes on IoT devices, limited resources, and diversity of the architectures. First, this work has been published last year at ACSAC. Here it's a kind of extension, and also a poster has been published. We are not used to in the academic community to get some fame, because we get some article after we publish the papers. So it was kind of funny, because it's really never happened I never heard about this in the academic community. So it was really funny. Only one contacted us to get information. And the bad thing is a lot of ones take the papers, write the text, but did not read the papers. Because some of them say that we were using a Raspberry to detect malware on your own computer. We do not do that at all. Please read the paper or read the article. Yeah, not all the websites that saying that you are doing detections on computers using Raspberry. Not at all. Yeah, it's what we did. Concretely, everything is open source, the data and the codes. So first we did an acquisition. We take samples, malware samples. We did some reverse engineering. This have been done by Pham, because he was malware analyst before, starting his PhD. Then we put on a Raspberry, we put an antenna, we execute the malware, we record the data, we do some pre-processing. I will explain and go deeper in the pre-processing. And after, we use some well-known classification algorithm to see if the EM emanation can help us to determine which malware is executing on the target. It's classification, not detection yet. And going to the data set. So which malware did we use? We tried to take we took real world malwares. Pham did some review of the code to understand what were going on the malware. So here it's all the malware we used, Mirai, Bashlight for the DDoS, the ransomware with GonnaCry, and 2 rootkits with a key sniffer, Keysney, that now is named Spy, and Make-It. So for the DDoS, the reverse reveals that there is CNC communication, TCP, UDP flooding, and bot killer and evasion techniques. For GonnaCry, there is P2 and C versions, and it will target some valid extension in the home folders. And also some variants, because GonnaCry usually the first version was using Blowfish to encrypt. And we took also AES and DES for the others. And the 2 rootkit, it's a keylogger, and also backdoor process hiding for Make-It. And additionally to these malwares, to these samples, we apply some obfuscation techniques that making the work of analyst even harder, because sometimes he even can't analyze malware due to some bogus control flow, opaque predicates, flattening or packers, or virtualization. We use this on the malwares, and we also put it in our dataset. So for each samples, we applied some of this obfuscation, and so it's a new binary that we have at the end, and we execute this. Here, it's the whole dataset we have. It's like 35 distinct binaries that we will execute. We have the benign to get like some reference. It's 30, we have, as a benign, we have 34 distinct random executions of usual Linux binaries. Also, we plug a camera to take pictures and record video and play audio. For Mirai, we have 8 distinct variations of the malware. So at the back, there's a light flattening, PCF, C-flatten, etc. For GonnaCry, we have all these distinct variations, and for all these distinct cryptographic algorithms that are used. So AES, DES, and when it's not specified, it's Blowfish. Then we have the rootkits and the bashlight with also distinct obfuscation techniques. Here, the 2 distinct targets we used. In the paper, there is only the Raspberry. Here, and after we extend to the MIPS in order to see if it works as well or not on the MIPS. And also, since we want to do some proof of concept, we have some demo. So first I'm running a camera because we initially planned to bring the things, but since I'm alone today, it was a bit hard to bring everything and to be sure that it would work. So we just plug a camera in our lab and I will try to stream. And also I will connect to the computer. Oh. Better with a good. And then to the targets. I'm still waiting for the camera that is still running, it's still trying to run. Here I'm on the CI20. So if we take the picture, on the right. I'm directly connecting on it here. And the example that we take is I will just execute 2 distinct binaries, GonnaCry, and the packed version of GonnaCry for the AES version. Oh, it will appear. So first, I will try to, I will do another connection. So yeah, first I'm connecting to the, I will just init in order to get like the data in the home, that they are not encrypted at all. It's doing it. The only thing we will see on the left is the blinking of the light on the target. And just also to explain the setup we have. So the target in the center, the MIPS CI20, and the picoscope that is it's an oscilloscope but without any screen, and also an amplifier plugged to the picoscope and the EM antenna above the CPU that we are targeting. So yeah, now let's execute the GonnaCry. Oh, I forgot to show you. That is where so now, if I go to the target of GonnaCry, we will see that it's encrypted some valid extension. I wanted initially to show that it were not encrypted at the beginning, but I can do it, just reinitiated the thing, and we will see that the target there is no encryption at all. In the LS, now there is no encrypted files anymore. So now, let's try to do an acquisition. So I say that I will run the acquisitions on WannaCry. And here it's what I will do with this command. I will not say too much about the command I'm running, because it will take too much time to explain each step, but most of the thing, it should be at the top, but we run our script. I say how many traces. I'm trying to get 10 traces of each of them. So the files, here it's saying which files we are doing. So it's WannaCry with AES and WannaCry with AES and UPX. So the packing version of WannaCry. Let's run and hope it will work. So we will see the blinking, I hope, on the left. That's saying that we are recording the thing. The EM traces. It should take a bit of time, but we will not wait all the time. Just want that at least one trace come. Yeah, one trace, and it should bring at some point if, yeah. Nice. It works. I will not wait the 20 traces come, because in 3 minutes we'll come back later. So we are recording. Here it's not in live. And what we are recording. So we have raw traces. I will show when the generation will be done. I will download it on my own computer and show you what is the raw traces. But here it's the main thing we did. So we have here traces. It's pretty huge data set, more than 2 terabytes. It's 2.5 seconds of recording for each executed binaries. But at the beginning, when we try with the raw traces, directly putting in any classification algorithm, we get no results. So we investigate a bit the data we get. And we went to the time frequency representation to see if there is something happen. And since we are targeting kind of complex environment, because on the 2 targets, it's a full Linux distribution that is running. It's an Ubuntu, I don't remember the version, but a full complex OS that is running. And so the accuracy when we execute the malware, it's not so yeah, we do not have any real accuracy, even with a good trigger, it's not really accurate. So what we did, we made an STFT to get the spectrogram on the right, where we have the time, and on the frequency, that the values are wrong. Sorry, for the 2, it's not the right value for the frequency, but it's in hertz. And each dot gave the amplitude of the signal for each frequency of the time. We have a pretty huge window and also a pretty huge overlap. This is due to get like, it was motivated initially to by the non-accurate trigger we had, or the complex environment we had, in order to compress the information, and after that the classification algorithm can classify the information we wanted. Let's go back to the, it's not finished yet, but it will finish. I will download what we have so far. So here I will just download on my own computer the data we just finished. So I will download the data. It may take time, but I can, at least when the first one will be downloaded, I can display it. I did not expect it so much time. Hopefully I already have data on my own computer. So let's display a first trace. Here I will just display the trace, one trace we downloaded. I did it this morning. Without Python, it will not work. And here it's a raw data we recorded. So the 2.5 seconds and the amplitude of the signal we recorded. But using this, we did not manage to do any classification. That's why we moved to the STFT. Here it's the STFT of the trace I just showed before. So on the right, it's just the metric I will use after. It's just the mean, the max, and the average, the standard deviation, and the max. The max in blue, the standard deviation in green, and in orange, it's the mean. And same for above, but over the time. So here I do over the time and on the top of the frequency. But due to the size of this, due to the size of the window, the time of the recording, the data were pretty huge, so does not fit well in classification algorithm. So the second step, it's something that we are used to in side channel community, it's feature extractions to find which bandwidths or channels are leaking more. Because due to the, once again, due to the trigger, we extracted some entire bandwidth and not just some time part of the signal. And for this, we used an NICV that is known in the side channel community a feature selections techniques based on the mean and the variations of the groups we have. So the groups could be the type of the malware or the malware itself, the binary or the family. I will explain what I call family type of thing after. But the idea is, if we go there, it's to find a number, some bandwidth that can leak and extract it, and after just do the classification on this using the NICV. And here it's what we have when we apply the NICV. On the right, here it's the NICV. So we can find that there is some bandwidth that are leaking more than the other, seems to leak more than the others. And if we look to the time, we have a really huge one at the beginning at around 1 second. Because Mirai is sleeping 1 second before his execution. Then, when we have this data, we applied the two distinct classification algorithms, two deep learning algorithms. In the paper, we also use more machine learning techniques, so SVM and naive Bayesian, but I will not show any result about this today. I will just focus on MLP and CNN, on the two targets. So the first scenario we did, it's the type of the malware. So here it's the compositions of what we try to identify. In this scenario, the algorithm already seen the samples it will have in the testing. Obviously, we do not learn on the testing data. We split everything, but the samples that are composed the data are the same. And here it's how the data is composed for the learning and the testing. So we have all the benign, the DDoS, the ransomware, and the rootkit. For the DDoS, there is Bashlight and Mirai. For ransomware, all the version of GonnaCry and the two rootkit for rootkits. And we can see that the CNN get the best accuracy with 99 and 99.95 for the CI20. And between brackets, it's the numbers of bandwidths that we use to get this information. because we did some experiments, initially just trying one bandwidth, another one, sorted by the NICV values. And after we move to an hill climbing algorithm, like we take the best bandwidth or channels with the highest NICV value, we try to classify, we add one, we try to classify. If we get a better score, we continue with these two bandwidths, and etc. And the 4, it's the number of distinct labels we can have in order to compare with the random classification. Here we are far from random classification. Then the second is with family. Can we say when a malware is executed on our target, which family this malware belongs to? And here we still have benign, Mirai, gonna cry, make it and here it's split it, make it and spy are not in the same level, and bashlight. So here we have the 6 distinct labels, and we can reach pretty high score. You can see that the CNN for CI20 is decreasing. So we are better, we can classify better with, classification is better down with on the Raspberry than on the CI20. Then, because here we are doing only classification, but what happens if our models that we computed for the testing see one sample that they never see before during the learning? What we did, it's the compositions of the learning dataset, and here the compositions of the testing dataset. So for benign, both are the same. But for Mirai, we have distinct variations. So we have the Mirai, the usual Mirai, 3 distinct variations. And for the testing, we had other 4 distinct variations. Same for GonnaCry. For rootkit, in one hand, we put, in the learning, we put make it. And on the testing, we put Kisney. And for bashlight, there is 2 variations that are not in the learning. And here we can reach pretty high accuracy, so 99, and the MLP get better score than CNN for Raspberry. And we use only 11 bandwidths for the Raspberry and 25 for the CNN. It's kind of optimal selection of the bandwidth to get the results we have. Then for virtualization, our algorithm can we say if malware is virtualized or not during its the malware that we are executing is virtualized or not. So we have the Mirai, GonnaCry, and bashlight without any virtualization, and the virtualized version on the right. So the 2 distinct labels. It works for the Raspberry, and it does not work almost does not work for the CI20, because the random classification, it's 1/2, and here it's only 59% of accuracy, so we are pretty near from the random classification. Then with Packer, same as virtualization, but with Packer. So the packed version and the not packed version and the packed version for the 2 labels. Only 2 class, and here it works pretty well with the MLP, but the CNN can't converge at all. So the TNN cannot converge for this classification on the CI20, but for the Raspberry, we can have pretty high accuracies at 92%. With obfuscation, here the 2 lines does not mean that we have distinct distribution between the learning and the testing. It's just because it does not fit on one line. So we have the distinct obfuscation techniques we use during to create our new malwares. So we have 7 distinct classes with the flattened, virtualized, data pack, C-flattened, UPX, sub, and PCF. On CNN, it works pretty well. And Raspberry, it works pretty well, but on the CI20, we can't converge at all, once again. So it seems that it's ordered on CI20 to converge to determine which obfuscation have been applied. And the last classification we tried, it's, okay, we have 34 distinct binaries. Can we determine which binaries is executed? We have a pretty high score with the Raspberry, 77 for 35 distinct classes, so it's far from the random selection. It's much less for CI20. Even it's not the random classification here at all. And to the full results are here. So it's the resume of all the results we have so far. And can we classify the data we just downloaded if the download have been down? It seems down. Oh, I don't want to do this. And now that since it has been downloaded, it's row traces. So first I need to extract the data. So the bandwidth we want to extract, I need to extract the bandwidth. So I need to find the right codes for this. Okay, here what I will do is just giving the directory where the raw data are and convert it in extracted bandwidth. It was pretty quick. So now if we go to the directory, oh, it's not the 20 that we were expected. What does happen? Something wrong happens. That's whoa. Yeah, the downloading have not been done well, so we just have 3 traces. But can we classify these 3 traces? It's what we will try here. So with this command, I just go to the MLP. So it's giving the MLP model we computed, the model and the list of the traces that I just downloaded. Because when I extract it, I create a list that will be given to the classification algorithm. And yes, I need to Python again. So just running the classification. And if we go to the comments, we gave a log file. So if I go to this log file, it's empty. No. We did a mistake. And here, what we can see, we have 2 traces, and the accuracy, it was 1. So the 3 traces we downloaded, so 2 packed and 1 unpacked, have been well classified. It's not right unpacked and unpacked, but since we know that it were only 1 unpacked and 1 not packed and 1 packed, we can say that it was well classified. So executing a malware, just that I did 2 distinct malware and recording the data, we were able to classify and to say which version of this malware have been done. It was a toy example because we get only 2 malware, only for the learning and also for the testing. So it was a simple example, but the results I showed before were on much more complex data sets. So with the 35 distinct algorithms or for distinct labels also. If we go back to the presentation, if we conclude, so this work has been published at ACSAC. Everything is open source, the code for the acquisition, for the classification, everything is in Python. The data also is available, only the extracted bandwidth, but we plan to publish everything and only for the ARM version. For the MIPS we did not finish yet, so we did not put on internet yet, but it's planned to be done. And for future work, I would say that it's not only future work, because we are waiting for the review. A paper has been published. And what we wanted to do and what we did is we moved to software-defined radio to get like less expensive material than a picoscope. Even if a picoscope is not so expensive, it's still 10K or something, so not easy to do at home. Extend to rootkit detections and not classification anymore. So we found a way to do detection, and it works. I hope in few weeks you will have the proof with the paper, but we can trust me, it works well. And moving from classification to detection. And the last point that is not pointing here, and it's something I really want to do due to my side channel background, it's understanding why and how why we can classify this and which features it works. But with what we have here, it's pretty hard because the resolution of the acquisition we have is really low regarding the speed of the CPU. And also due to the STFT techniques that we have to use, that everything is compressed, so it's really hard to reverse and go back to the first trace and say where and why it's leaking. Thanks for your attention.